Good evening, because I'm recording now at 8 p.m. Welcome to our third lecture on YouTube, titled Introduction to Multiparameter Models. This topic will be divided, I think, into 4 parts. Hopefully they will be much shorter than usually or previously, and that will be our new standard because I tried to make it more granular. The first one probably will be a bit longer, and then we'll see how it will go. I'll try to keep it under 45 minutes, but we'll see what happens. Generally, we've kind of exhausted whatever we could say about single parameter models, which we in our last 2 recordings. However, what we are we'll be doing now is discussing models that require more than one parameters, which will lead us to more complicated models of actual processes or relationships that we are interested in. So, without further ado, what do we mean by multiple parameters? Multiple parameters, we have multiple unknown or unobservable quantities. For example, in electrical circuits, it would be parameters of circuit we are interested in. In kind of social relationships, we would like to know what are the influences of particular actors on the outcome. In case of COVID-19, we would be interested in modeling of infection rates or death rates or transmission rates. All those parameters are interacting each other in order to create our model. However, in many cases we are mostly interested in only a few parameters, because that happens when our model is complicated and we want to find out certain quantities of interest. For example, in COVID-19 modeling, we might be interested in the prediction of new infections. We maybe are not that interested in particular parameters regarding transmissions, at least not for current purposes, but we would like to get those parameters that we're interested in. And for that, there's an advantage of Bayesian statistics. We can marginalize it. So we can take our joint distribution of measurements and parameters and extract from that extract from that only the values that we have. However, with all the consequences of having a marginal distribution. So we can generally split our parameter vectors into parameter of interest and nuisance parameters. Nuisance, that means those are just obfuscating our view. So generally, we can split our vector. If we assume that parameters constitute a vector, we can split this vector into θ1 and θ2. And for example, in normal distribution, we might be interested only in mean value. So what is the expected value, for example, of mentioned infections, and we're not that interested in the variance or standard deviation of the distribution. Formally, having our joint posterior density, that is proportional to the likelihood times prior on our parameters, we can average this distribution over the nuisance parameters. So in a way, we can integrate those parameters out of the equations. This is, of course, formal statement of the problem. Formal, that is, we won't be computing such integrals in most of cases. Why? Because general integration is hard, and analytical integration is very hard, and getting multi-value integrals of anything except absolutely basic functions is extremely difficult. So what we will be doing, we will be taking samples of our distributions in order to marginalize our distribution by sampling. And what is the marginal distribution anyway? This, in case of our posterior distribution of interest, so distribution of vector θ1, parameters of interest, conditional on our measurements, it is a mixture of conditional posterior distribution given our nuisance parameters with a weighting function that is the distribution of possible values of theta2. So we can kind of averaging our distribution, assuming certain weights depending on how probable are certain values of theta2. So we want to remove theta2 by averaging the results. So we are kind of creating, as usually in Bayesian statistics, we are creating a compromise between data and the prior knowledge. And theta2 can be either simple parameters with continuous values, or it can be a discrete parameter which can be interpreted as a multiple submodels. So we will be integrating or summing out values of parameters depending on multiple different models. Usually we do not compute marginal distribution directly, but we get them from sampling. So that's what we'll be doing in multiple cases. So let's start with the most basic concept, so normal distribution. Normal distribution you should already know from multiple accelerated statistics, and which is a distribution that is uniquely defined by its mean and variance. At first we will focus on an independent observation from the univariate normal distribution. So normal distribution of one variable dependent on two parameters. Everyone knows the bell-shaped curve, and we are starting with very non-informative prior distributions. Generally, non-informative distributions for normal case can be defined in multiple ways. However, if we go strictly non-informative, we need to assume that any value of me is possible. So we can assume a uniform probability, which we will generally won't be doing in more complicated cases. But this is useful for analytical computation because it will be much easier for us. And we assume that any scale is possible. So our variance, we don't know is this variance of 1% or thousands of percent, or so in order to get any possible scale of our variance, we do not focus, or standard deviation in this case, we do not focus on the we cannot put uniform distribution for that, because that won't give us all possible scales, because scales can differ by order of magnitude. However, if we assume that a logarithm is uniform, a logarithm of standard deviation is uniformly distributed, then we have access to all possible scales. All orders of magnitudes can be easily realized. And returning to normal variables, our distribution for mean and variance could be the uniform proportional to uniform distribution. So uniform, so a constant probability for all values of me, and the function of 1 divided by sigma squared for the variance components. What we have here is a standard non-informative prior that can be derived from Jeffrey's prior, so-called Jeffrey's prior, which is a historically very important result of times when we didn't want to use any information in priors if it wasn't absolutely necessary. The main flaw of this approach is that our unbounded uniform prior for mean and this prior for variance is not proper. That is, it won't integrate to 1, and it can cause certain issues in general cases. That's why, among the others, they are now being discouraged from using. We can use different non-informative prior, or almost as non-informative, but practically not introducing any issues to our computation. But that we'll do later in discussing this topic. However, having such form of prior for our two parameters, as you see, because me is uniform, it does not is not presented directly in the formula. We can do some computation, and here we can see how it generally looks like. So, in order to get to our n measurements, our likelihood consists of multiple values of exponential of normal distribution. Because each of these events, their products are multiplied by each other, so in each of the instances is assumed, we can be assumed independently distributed. We can compute each of our likelihood is a multiplication of likelihoods for each of the samples. And because our normal distribution is exponential distributions, we can use the option of multiplying multiple normal distributions by each other by getting in an exponent a sum of all those exponents. Because we have the same base, so multiplication of multiple exponential functions with the same base results in an exponent of sum of those. It is a base up to the power of sum of exponents. And what you had here, in case of our normal distribution, we always have the term of 1 divided by sigma times a certain constant related to square root and pi, and we have sigma squared in the likelihood, in the normal likelihood. So we get our prior, which is represented here by -2, and we get this form. What is important that we can see here, we can decompose this sum into certain useful components. First of all, we can express all our measurements in the form of y bar, which is the empirical mean of all our measurements. So we take an arithmetic mean, or empirical arithmetic mean of our measurements, and we get function y bar. Simple computation shows us that this sum can be decomposed by differences between our measurements and y bar squared plus n, so number of measurements, times y bar minus me, so our mean of our distribution, also squared. And that term is related by n minus 1 to an estimator of variance. So we can get the standard estimate of variance, so s squared in this case will be the average, but with n minus 1 division of measurement minus the expected mean value. So this is the estimator of variance, this is the estimator of mean, and those two values, so y bar and s squared, are so-called sufficient statistics of normal distribution. As you can see, all the information required for estimation of those parameters, by using no advanced tricks here, just by simple multiplications, can be represented by those two values. So we don't have to, considering this model, we don't have to analyze each data point separately. We can just represent them by mean and variance estimators from our data. So those sufficient statistics will be enough to do all our computation, which is useful because it leads us to some kind of analytical result, and also gives basis for multiple different computations. So our J-posterior distribution is really dependent only on those sufficient statistics. It is not, we don't have to use dependence on the entire data. So only on two values, two numerical values, we can get our distribution of our parameters will be. Our posterior distribution is dependent of sigma and me is dependent only on those two parameters of our data set. So what we can actually do here, we can do some kind of factorization of our joint posterior distribution to even improve our analytical result, because we can rather directly obtain the marginal posterior for sigma squared. Sigma squared is this value that we are not that interested in. We, however, would need that in order to use the conditional posterior distribution of me, because our me will be conditional on sigma squared and conditional on measurements. In order to integrate sigma squares from this equation, we will need the posterior distribution, so sigma squared conditional on measurements of our variance. So this can be expressed as this integral by integrating out the mean, which is kind of counterintuitive in what we are doing, but we are doing analytical computation here. We are not going for numerical results yet. So, why we want to do such things? Because this can be observed that this is a so-called normal integral. So this is something that can be computed because it's really integral of a certain slightly modified normal distribution dependent on sigma squared. Sigma is not a variable in this integration, so certain things can be turned out of the equation, and this becomes a integral on the entire support, so minus plus infinity of normal distribution, which is known to be 1 or with certain parameters scaled thing. So this will be this thing can be scaled out and because can be integrated out. So because of that, we can get directly the equation for it can be directly into this formula, which is a scaled form on so-called inverse chi-squared distribution, which can be useful because inverse chi-squared distribution can be is usually implemented in multiple numerical libraries, and because of that it can be easily sampled from or can be analyzed by numerical computation without any problems. So we can from this derivation we get that our sigma squared is distributed conditional on y is distributed as inverse chi-squared parameterized by our variance estimator s squared. So as again, only one sufficient statistic is needed in order to get the distribution, the marginal distribution of sigma squared. And this factorization, so expressing our joint posterior as a multiplication of me dependent on the sigma squared and y, so our normal distribution, which we can see here because this is a normal distribution dependent on sigma squared, and getting distribution of sigma squared conditional on measurements, we can do things like we can sample sigma squared from its probability, which is again known by inverse chi-squared, and then we can draw me from our normal distribution conditional on sigma squared. So this will get us the values of our this will get us values from values from me, and repeated simulation, so from multiple repeated sampling, first from sigma squared distribution, then from me, we get values of me so we could get values of me marginalized over sigma squared. So without analytical integration, we can perform this marginalization. But in this special case, which again we a special case of special case, we can see that this problem is also analytically solvable, because our original distribution can be integrated by a certain substitution, in this case using substitution of z instead of sigma squared scaled by the and me squared by this value, but for integration by a sigma squared. So we will be integrating our joint posterior distribution for me and sigma squared, integrating by sigma squared, and doing this substitution for sigma squared. So z equal constant but dependent on me divided by 2 sigma squared. We can get relatively simple integration of z to a certain power time exponent, which after certain computation leads us to especially that this part is really this part is not independent on me, because me can be removed out of our equation here. So this integration will be just a number, so we are left again with only A. It becomes so-called student's t distribution, which we'll be returning today to it later. And this this thing with n-1 degrees of freedom, so the more samples the result is higher. The t distribution with n going to infinity becomes again a normal distribution, but this is a result which are not interested too much today. But again, we can get our results, so our marginal distribution of me, as a student's t distribution conditional only on sufficient statistics of the data. And because of that, we can perform one more thing. We can perform a posterior predictive distribution for a future observation, so we can estimate our future observation, which things we will be doing. We are doing our previous lecture with binomials and with Poisson distributions. We can predict new values conditional on just on the previous outputs, and this can be of course done by double integration of the of our previous samples. So the first two factors of inner integrals is just the normal distribution for future observation given by the values of me and sigma squared, and does not depend on previous measurements, which is very good situation because there is kind of hidden in the previous conditionals. So there is no direct influence on y wave or y tidal on measured y. So we just have on those two parameters. So because our measurements are independently distributed with this distribution. So really, in order to perform predictive distribution, we just need to sample from our posterior for me and sigma, and then we can simulate our values of y. And we will be doing it again with different examples today, or during this topic. So this is part of the theory, how we are working here. We can derive certain analytical results, but those analytical results are not really what we are interested in in this course, because analytical results are very nice, but only for limited, simple problems that we really won't encounter in real life. So we'll just now focus on how to model this problem in STAN and see how it's working. So let's skip certain, again, toys with the terminal and just focus on our problem. Let's focus on so-called Newcomb's experiment. Newcomb experiment was an experiment in 1882 of measuring the speed of light. Newcomb has measured the amount of time required for the light to travel a distance of 7,442 meters, and there is a set of measurements. We'll observe it in a moment. There are 66 measurements, which we will try to use a normal model, so estimate with certain measures of uncertainty of our getting a normal distribution in order to estimate the speed of light, which will be represented for us by a marginal distribution of me. And because in this case our result works here, because this distribution is student distribution with 65 degrees of freedom, because we have 66 measurements minus 1. Degrees of freedom is a parameter of the distribution. We will see which you can see is represented here. This is n. So it's influencing the shape of our distribution, and especially its tails. So we have our sufficient statistics. So we have the y bar, which is 26.2, and as sample standard deviation is s is equal to 10.8. So we can square it if necessary. And so assuming, again, non-informative prior distribution for me and sigma, we can get the 95% central posterior interval for me. We can obtain it here. And our data looks differently, because as you can see, mean is 26.2. What does it mean? It means that the data is recorded as deviations from 24,800 nanoseconds. So we had, this was a reference value, and we are just looking at the difference from this. And we will compare these analytical results with what we can do with stand model. So again, some packages, we will be skipping it in the future. You can see it again on GitHub, and we get our data. The data, you will be provided the data with this in the file light.txt, which is it will be in the Newcomb folder in the multiparameter models in the repository. As you can see, it's a light.txt file, and which will be again, you won't have the cached models before as before, so you'll have to compile yourself to see how it works. And what we are doing here, we're just reading the table, which is in a text file. This text file is, as you can see, unformatted, just numbers, positive and negative integers. And what we'll be doing here, we're just making a histogram. And this histogram, which could be a bit prettier, but let's don't focus on that too much. And the histogram of Newcomb measurements is interesting because we have two very low measurements, and the rest of them is kind of normally distributed. We start with assuming a normal model, and then we will see what's going on. And I created a model which works like this. We have the as the data we get number of samples and our measurements. We will, in this case, just to be brief, because we have a lot of theory, we won't be discussing prior checks. We will do it in our next example. But for this case, we just start with a model. Our model has two parameters, sigma and me. So we will be estimating both standard deviation of our distribution of our model, standard deviation of our model, and its expectation. And we will be having these parameters. Me can be a real number, sigma has to be positive, and we created our model. And this is something new which you haven't seen before, because previously we created our stand models using so-called sampling statements. So we defined how certain parameter is distributed. Now we are defining the our distribution as the we are defining our distribution as logarithmic as a logarithm of joint posterior distribution. Because of that, this is formally identical situation. As you can see, it's getting darker and darker in my place because night is coming. Either way, what we have here, our model is normal likelihood and this uninformative sigma 1 by sigma squared distribution. In order to do so, to specify this our model using logarithmic likelihood, logarithmic, we need to add logarithms of all the terms of our posterior distribution. So we'll take our original model, which is generally here, and we have our prior, and we have our likelihood. And we take logarithms of all those things, and we will be adding additional elements of that. So in this case, our exponential sum will be just a sum of normal likelihoods for each of samples independently, and our likelihood will be just our prior will be just a logarithm of sigma squared. So it will be of -2 times logarithm of sigma plus. And there's special functions defined for all distributions implemented in stan. So it will be normal LPDF, so logarithmic probability distribution function of y, so our measurements, so here, conditional on mu and sigma. Here we have a nice bonus of vectorization of this data, so we will be able to do some such things. We don't focus on the generated quantities here because those we'll be using it for later cases. So this you can ignore here. We just specified the so-called logarithmic likelihood of our model, and we're getting some samples of me, but that was needed for some other tests. So we generate our new data. In order to fit our model, our data will be n, so it will be number of samples, so length of our data set, and our data set, because we have only one parameter. So we perform some fitting. Again, we call the our model, which was compiled by stan utility earlier. We send provide the data. We provide it with seed. Remember, providing seed is very important. Doing computation, no problems happens, and we extract our parameters of our model with function extract, and we start. Let's do some plotting. And what is the problem? The problem that we can observe here is that actual speed of light is somewhere here. And our model locates its mean somewhere here. In particular, at 26.2, 95% confidence interval is 23.56 to 28.87. And comparing it to analytical results, we get what we were expected to get. So numerical result is equal to the analytical result, which is okay. But let's try to tweak it a bit, because generally the problem with outliers is that normal distributions are very sensitive to outliers. Why? Because normal distributions have very thin tails, or very light. It's called light tail. So almost all the probability of normal distribution is here. In the tails, these values are very small. So when data happens far away from the mean, then it suggests our model that something is wrong, that mean is somewhere else. So there's a very large sensitivity for that. And that, of course, has for sure drawn us from our actual speed of light. So our Gaussian model is biased by our outliers. So what can we really do? We can change our model. We can change our model to a model that allows for outliers. So a model that needs a heavier tails that will allow that, okay, some probability of something happening here. This leads us to the areas of robust estimation or robust regression in certain cases. So this will be something that will allow us to get estimates which won't be influenced by outliers so strongly. And we won't be discussing too much here, but just I wanted to give you certain highlights. What can we do in stan with relative ease? We can start to do some robust inference with student t likelihood. So what actually is going on here? Student t distribution is a distribution characterized by three parameters: degrees of freedom, location, and scale. In case of degrees of freedom, control how thick the tails are, how heavy they are, how much probability is hidden in tails. The lower numbers of degrees of freedom, the thicker the tails. If they go to infinity, we get approaching normal distribution. Location is similar to mean. This is a location of the mode of the distribution, depending on the number of degrees of freedom. Student distribution might not have a mean at all, at least in the sense of is an operating integral. And the scale is equivalent of variance, so how spread is this distribution. And here we have one bit problem. We had an informative mean for me and for sigma by using uniforms inappropriate scales. However, we don't have any informative prior for degrees of freedom. And generally, in such cases, such priors should allow a situation of degrees of freedom going high. Why? Because that would suggest that we would like to have a prior that won't enforce us to different model. It will just give certain possibility that our model might be normally distributed. So it might allow us going number of degrees of freedom up to infinity. And selecting proper priors is difficult access. However, there are certain resources we can have. For example, at StanWiki, we have a page called Prior Choice Recommendation, and there is a suggestion of using a non-informative prior for degrees of freedom, which is a gamma distribution parameters by 2 and 0.1. And this value allows, it's not, there are other options. For example, using theory of penalized complexity priors, we can do something else. Maybe we'll discuss it later during the course. However, especially during hierarchical modeling, however, in this case, we need to provide certain distribution, and this distribution is relatively well regarded in as an analysis option. So what our models now looks like. Not much changes, except that one new parameters happen here. This is degrees of freedom, again bounded from 0. And we have our model, which in our model we've changed the likelihood to student t LPDF. So it's again we are working with logarithms. Because of this uninformative prior for sigma, we still have to use logarithms. We cannot use sampling statement because 1 by sigma squared distribution, first of all, is not a proper distribution. It cannot be given this way. And other thing, it can be used, in this case, we can provide it easily. And we are adding another factor d, which will, in normal form, it will be a factor. So the probability of degrees of freedom, value of degrees of freedom, but in this case we are adding a logarithm of it, so we are adding gamma LPDF for our parameter ni to 0 with parameters to 0.1. Again, this part we won't be discussing at the moment here because it's not it won't be useful for our analysis. And what we are doing here, again, compilation, we fit our model using the using stan, providing with the same data as before because nothing changes in this regard. We provide it with seed, everything works very nice. We get our parameters and we can get another histogram. And what's happened here? Well, our outliers aren't changed. We have not got speed of light correctly anyway. Why? First of all, the experiment was bad. This is an old experiment from the 19th century. And there are certain we have improved over our Gaussian model because, as you can see here, the mean of Gaussian model is on the left of the location of our mode of our distribution. In this case, the mean of our marginal distribution for the me, so for our, the speed of light from our model really is at 27.42. The result that would be actually good for us would be 33, so it still is outside of our confidence interval, but we've got from our model more. We got a tighter confidence interval, moved in right direction, but it is still biased by the quality of experiment. As you can see, the experiment was very spread. It included the right value, but it wasn't well represented. So really, this is something that you had before in multiple cases, garbage in, garbage out. We got bad data and we cannot do anything with bad data, especially without proper information. If we had good information on the actual speed of light, then we could we could have an informative prior, especially for mean and for our scale. Then we have something completely different situation, because in that situation we could be able to improve this, but we didn't have possess proper expert knowledge at this moment in order to improve our results. And this will be for this part of our lecture. And next part we'll discuss different multi-parameter distribution. It will be a multi-normal distribution. Then we'll move to a multivariate normal distribution. So we'll go to multiple parameters and explanation covariance, and we'll finalize probably in the fourth part with the more advanced case of multi-parameter model, strongly nonlinear. Things will be happening more complicated, and we'll discuss that in a few days. I plan to release parts of these lectures every 1 or 2 days away from each other. The first one probably will arrive on, so we will see it on Sunday of 17th of May, and the rest we'll see how it will go. So thank you for listening of this shorter part this time, and have a nice night.